Up to this point, the addition reactions that we've talked about could be classified as Markovnikov or anti-Markovnikov. Remember, if we're thinking about Markovnikov or anti-Markovnikov, if we're thinking about these conditions, what that implies is that the thing that we're adding across the double bond is going to take this form, H and something else. Okay, so now going forward, none of the reactions that we'll talk about can be classified as Markovnikov or anti-Markovnikov reactions. So let's start by looking at the addition of a halogen or halogens and water. They're going to follow, both of these reactions are going to follow pretty much the same mechanism with a minor variation that you've already seen. So we'll look at that. Let's take a look at the products that you would get. So if you add a halogen, and the typical halogens are chlorine, bromine, and iodine. If you add a halogen across an alkene, each of the alkene carbons gets one of the halogen atoms, and what you've made is called a vicinal dihalide. The term vicinal means neighboring. Okay, so this vicinal dihalide is one where the halogen atoms are on neighboring carbons. If instead of just the halogen, you also have some water in the reaction mixture, then you're going to get a structure shown to the right, which is called a vicinal halohydrin. Now this has a particular regiochemistry associated with it. So we're going to note that, but then we're also going to talk about it when we look at the mechanism. So notice that the OH, you're adding an OH and an X. The OH attaches always to the more substituted alkene carbon. And the halogen attaches to the less substituted carbon. Okay, so the first thing that we're going to do is look at the mechanism, talk a little bit about the mechanism, and then we're going to look at the stereochemical outcome of this reaction the way we did hydroboration oxidation. So the mechanism. So let's use this alkene and react it with chlorine. So with all of these reactions, what we've seen is that the pi electrons in the alkene are weakly nucleophilic. That makes the chlorine molecule itself an electrophile. Now chlorine, molecular chlorine, is nonpolar. But at any given instant in time, there can be a transient dipole in the bond between the two chlorines, making one of them partial positive and the other partial negative. That's especially true if the chlorine molecule finds itself in the vicinity of the pi electrons in the alkene. So that's going to cause that transient fluctuation to occur. So now one of the chlorines, the one that's closer, has a partial positive charge, the other has partial negative. And so what happens at this instance is that the alkene pi electrons form a bond to the chlorine with a partial positive charge. That's going to cause the bond to break toward the other chlorine. The chlorine that it was attacked originally attacks back. Now the result of those arrows give us this structure here. A three-membered ring with two carbons and an atom that's not a carbon, so a heteroatom, with a positive charge associated with the ring. We also have a chloride ion that was released in that first step, so that's hanging around. The structure that we just made, this little three-membered ring, is called a halonium ion from halogen. This one specifically is called a chloronium ion. We've seen this pattern before. Three-membered ring, two atoms that are carbons, one that's not, positive charge. We know in cases like this that nucleophiles attack the more substituted ring carbon. The nucleophile in this case is the chloride ion. That makes the halonium ion the electrophile. So the chloride ion will attack at the more substituted carbon, which causes the ring to open. So the result of all this is the vicinal dihalide. Okay, so let me highlight this bond right over here in the halonium ion. Notice that it was the other bond that broke, so that highlighted bond remains intact. That's why we have a chlorine attached over there on the right. Okay, so the chloride ion was the nucleophile. That makes the halonium ion the electrophile. And there was a part of the molecule that moved away from the carbon that got attacked. That was the chlorine with the positive charge. That's called a leaving group. So this second step, where the chloride ion attacks the carbon and breaks open the ring, that second step has a mechanistic name. It's a substitution because you're substituting one chlorine for another one. Or in more general terms, you're substituting a nucleophile for a leaving group. The second step here is called an SN2 step. That stands for bimolecular substitution. And we're going to be looking at the details in our next packet of notes. But for now, what we need to know is that in an SN2 reaction, or in an SN2 step in a more complicated reaction, a nucleophile, we'll abbreviate as NUC, attacks, that is to say bonds with, a carbon that has a leaving group. And replaces it. So the general pattern is shown in this little schematic. A nucleophile attacking an electrophile. So it attacks the carbon that has the leaving group. So this is the electrophile. We'll say E+ for electrophile. It attacks the carbon that has a leaving group, and we'll learn about leaving groups in the next packet as well, and replaces it. The leaving group ends up going out on its own. Now in the case up above, the only reason that the leaving group didn't completely go out on its own and depart entirely from the molecule was because it was still tethered by another bond to the rest of the molecule. But in most cases, the leaving group is going to detach from the entire molecule that got attacked and exist by itself in solution. Okay, that's the general idea of the mechanism. Now we're going to see an example of the mechanism when you have water involved. We'll do that on the next page when we start looking at the stereochemistry. So let's take a look at the stereochemical outcome of this. When we looked at hydroboration oxidation, we saw that that was what was called a synaddition. The H and the OH attached to the same face of the alkene, whether that was the front face or the back face. In this case, the addition of either halogen or halogen with water is called an anti-addition. That means that whatever elements we're attaching are attaching to opposite faces of the alkene. So when we draw the product, one of them is going to come forward and the other one's going to go back. And so in the structures shown in the box, notice the variation. So in the first product, the X is coming forward, the Y is going back. In the other product, at the same carbon, the X is going back, but the Y is coming forward. So let's take the reaction that we just learned about, draw some more mechanisms, predict some products, learn some more things about SN2, and then be able to draw products for these things. So first of all, remember what we did with hydroboration oxidation is we assessed the optical activity of the starting materials. So the alkene, in this example, is achiral. Chlorine is achiral. So neither one of those is optically active. So we have optically inactive starting materials. And you know that what that means is that we're going to get optically inactive product. So let's draw the mechanism for this. So we're using chlorine as our halogen, but it could be bromine or iodine. So the alkene uses pi electrons to attack one of the chlorines. That causes the bond to break between the two chlorines. The chlorine that was attacked attacks back. Better. Okay, so you form a chloronium ion like we saw on the previous page. Now, the two bonds to the chlorine in that three-membered ring necessarily have to be on the same side or the same face. So they both have to be coming forward or going back. You can't have in a three-membered ring one of those bonds coming forward and the other bond going back. So the chloronium ion could form from the front face of the alkene. And in doing so, remember that the carbons in the alkene get rehybridized. Now they're sp3, and that's going to push the methyl group at the left carbon, the more substituted one, it's going to push that methyl group back. What's also happening is that the chloronium ion is forming from the back face, which is going to push the methyl group forward. And in both cases, there was a chloride ion that was released in that first step. So let's put those in as well, because this is the nucleophile, and so we need to have that in there. Okay, so this here is our nucleophile. The chloronium ion itself, the entire thing, is the electrophile. And this chlorine that's part of the molecule is the leaving group. Okay, so in the reaction, remember what happens is that the nucleophile attacks the more substituted carbon and opens the ring. It's going to do that in both of these structures. But there's a particular stereochemical outcome associated with the SN2 reaction. And so we need to understand what that is. So in an SN2 reaction, the nucleophile always attacks the carbon that has the leaving group from the side opposite the bond to the leaving group. So let's write that down and then talk about what that means. In an SN2 reaction, the nucleophile always attacks the carbon with the leaving group from the side opposite the carbon leaving group bond. All right, so what does that mean, and how do we accommodate that statement in the way that we draw the product of this step? So let's look at the chloronium ion on the left, okay, the one that has the bonds to the chlorine coming forward. When the chloride ion nucleophile attacks it, it's an SN2 reaction. So it attacks that carbon from the side opposite the bond to the leaving group. Now the bond to the leaving group from our perspective is coming forward. That means that the chloride ion, this guy right here, is attacking from behind the page. When it does that, it's going to end up pushing that methyl group forward. So the chloride ion came from behind. That ended up pushing the methyl group forward. And then the bond to the chlorine that's still attached, to the leaving group chlorine, we could call it, is still coming forward. So that would be this bond here. The same idea is in operation with the other chloronium ion reacting with the other chloride ion. The chloride ion in the other chloronium ion attacks opposite the bond to the leaving group, which in this case is going behind the page. That means that the chloride ion nucleophile came in from the front part, or from our point of view, the front of the page. So it came in from the front. That ends up pushing the methyl group back. And then the other bond stays back. Okay, so what did we end up with as products? So when we analyze this, what we find is that these are enantiomers. Because we're starting with an achiral alkene and we have achiral reagents that we're treating it with, there's no preference for one face or the other to be attacked preferentially. That's redundant. A preferential preference. Okay, never mind that. There's no preference for one face to get attacked over the other, which means that we're forming the enantiomers as a racemic mixture. And so once again, we notice that if we start with optically inactive starting materials, the result is optically inactive product. Okay, so for the next example, let's do something a little bit different. So we have not, as of yet, looked at a reaction involving a halogen and water. So let's change these conditions and make this bromine and water. Okay, the alkene itself is chiral, so it's optically active. So even though bromine and water are optically inactive, we have optical activity somewhere in our starting materials, and so we're going to expect that the product will also be optically active. Let's draw a mechanism and see how this works out. So the first part of the mechanism, the first step, is identical to what we've seen in the previous examples, except that we're using bromine instead of chlorine. So one of the bromines gets attacked, the Br-Br bond breaks, and the bromine that was originally attacked attacks back. Okay, we form a bromonium ion intermediate, which I'm going to draw largely without stereochemistry. Now remember, in this case, we don't just have bromine, so there's a bromide ion, but there's also water. So water is explicitly included in the reaction mixture, and we have far more of it than we do bromide ion. And so the water is going to act as the nucleophile. It attacks at the more substituted carbon, opens the ring, the two hydrogens and the lone pair that were also attached to the oxygen go along for the ride. So we've seen this pattern before. When water attacks something as a nucleophile, we usually end up with a picture like this. Another water molecule can complete the reaction by removing that extra proton. So we've seen this pattern before as well. For example, in the acid-catalyzed addition of water, so Markovnikov hydration of an alkene. Okay, so here, then, is the product. Okay, OH on the more substituted carbon, Br on the less. Now, if we were to incorporate stereochemistry in this, remember that there's going to be two bromonium ions. So this reaction goes through, let's say this reaction features two bromonium ions. So one of them, which formed from the front face, that would push the methyl group back. And then, of course, the other one that formed from the back face. And that pushes the methyl group forward. Both of those are going to get attacked by water in the fashion shown in the mechanism directly above those two structures. And the result is going to be a lot like what we saw in the previous example. So water attacks. We lose a proton. And we're going to end up with these two products. Notice that the methyl group at the bottom of the ring doesn't change its orientation. It's not directly involved in the mechanism. It's not directly involved in the reaction. It's not attached to any of the carbons that are undergoing reaction. So we end up with these two products. And once we compare them, we can tell that they are diastereomers. Use a different color that's going to show up a little better. These are diastereomers. And they form in unequal amounts. So we've made an optically active product, given that we started with optically active starting materials. The addition of halogens or halogens and water, these are examples of what are called stereospecific reactions. In a stereospecific reaction, the stereoisomer of the product that you get is dictated by the stereoisomer of the starting material that you began with. So a particular stereoisomer starting material gives a particular stereoisomer product. So for example, let's look at this pigeon problem, and I'm just going to show you the approach to it, and then you can work out the details on your own. So what we're doing is chlorinating two alkene isomers, the cis and trans version of 2-butene. So trans 2-butene and cis 2-butene. Because the reaction is stereospecific, we would expect to get a different product or products based on the reaction of one versus the reaction of the other. So to predict the products, remember you want to include all your H's. And then to draw them, we're going to have to vary the stereochemistry, the wedges and dashes. And so keep 3 bonds. I like to keep these 3 bonds in the plane. Like so. And then, and I'm going to just do this in a different color, and then you can vary what's going on at each of these carbons by including your wedges and dashes. Okay, so you'd want to predict the products, draw all the possible products, and then compare, assign R and S. That's going to make it easier to compare things, and then compare the two outcomes to one another. Doing so will allow you to prove that the addition of halogens or halogens in water is a stereospecific reaction. You should get a different stereoisomer product from the trans reaction than you do the reaction of the cis isomer.